We're going to look at three very similar functions. X to the power of something, where the something is a positive exponent. X squared, x cubed, and x to the fourth. And we're going to ask ourselves the same question each time. What happens to y when we increase the value of x by an itty-bitty amount? Okay, so we'll start with x squared. Our relationship here is y is equal to the square of x. Whatever x is, we square it, and that's y. So what happens when we nudge x up by an amount, an itsy-bitsy amount dx? Well, that's something that we can work out. We multiply it out, and we get this. Y plus dy equals x squared plus 2x times dx plus dx all squared. And now remember that dx all squared, remember from a previous video, where dx is an itsy-bitsy amount, dx all squared is an itsy-bitsy teensy-weensy amount. And we're just going to toss it out. Sorry, dx squared. So now we end up with y plus dy equals x squared plus 2x times dx. We'll pull the y out from both sides of the equation, which means take the y out of the left and the x squared out from the right. And now we have this dy equals 2x times dx. Rearrange, divide by dx, whatever you want to call it. And then our final is dy by dx equals 2x. And this is what we were looking for. We're making a general statement that at any point along this curve, the amount that y is increasing is equal to twice the value of x at that point. So, for example, let's use x equals 10. We're predicting here that the slope of the graph, the amount that it's increasing, is 2 times 10, which is 20 at that time. So at x equals 10, y equals 100. And then when we multiply that all out, and let's pretend that dx is 0.1, the little amount. When we multiply that all out, dx squared becomes a stupidly small amount. And that stupidly small amount we toss out. So dy by dx ends up being just 20, which is 2 times x, which is what we had figured out it would be. Now we'll do the same thing with x cubed. And this is where familiarity with the binomial theorem will come in handy. We're going to cube x plus dx, and we get a whole string of stuff. And we are going to toss out the second order of smallness, itsy-bitsy, teeny-weeny, and the third order of smallness, itsy-bitsy, teeny-weeny, tiny-whiny, wibbly-wobbly. Okay, and so we end up with y plus dy equals x cubed plus 3x squared times dx. We remove the y from the left and the x cubed from the right, do our fidgeting around, and we end up with dy by dx equals 3 times x squared. Now we're going to go right to the x to the fourth. Again, we nudge x up by a small amount dx. And then we multiply that binomial out, raise everything to the fourth power, and we end up with x to the fourth plus 4x cubed plus a bunch of stuff. We're going to keep the term without the dx. We're going to keep the term with the dx. But everything else, all the dx squared, dx cubed, dx to the fourth, they are getting so small, we don't count them. Doing what we did before, we end up with dy by dx equals 4x cubed. Okay, so here's the results of our little experimentation, okay, in this lovely table. When y is x squared, then dy by dx is 2x. When y was x cubed, dy by dx was 3x squared. And when y was x to the fourth, dy dy by dx was 4x cubed. And do we see a pattern in this? I'm going to conjecture that x to the power of something, when I want to find dy by dx, is x to the power of something minus 1, but all times the something. And we rewrite that with n's. And we seem to have a general rule. And we're going to run with that. But what if we want to use a negative power? We take advantage of our general binomial theorem for negative powers. So x to the negative 2, we'll nudge it up by an amount dx, and then apply the general binomial theorem. And we do the same as we have been doing. We keep everything up, every term with up to dx, and throw out every other term of diminishingly small, teensy weensiest, itsy bitsiest, tiny whiniest dx's. This is math talk. Again, remove the y and the x to the negative 2 from the picture, and we end up with dy by dx is negative 2 times x to the minus 3. Which is cool, because that fits with our conjecture. The conjecture that we conjectured previously. Okay, now let's try this for a fractional power. So we're going to do x to the power of a half. Nudge up x by an amount dx, expand it as much as we need to, because everything to the right of the 1/2 of dx over the square root of x has got increasing amounts of smallness, if that makes sense. So we're only going to keep these first two terms, okay? But then we'll take off the y on the left, and so the square root of x on the right, and we end up with dy by dx is 1/2 of x to the minus a half. And again, you can plug in numbers into any of these, and I would encourage that so that you can see what it looks like when we toss out the dx all squared and the dx cubed and all those tiny amounts. And then it's time to practice various incarnations of this very simple idea to see what it looks like. Hope you enjoyed this. Bob's your uncle. Say hi to Bob, and cheers.